There's a moment every morning that almost nobody thinks about. The sun comes up, light pours through the window, and you go about your day. But here's what you're actually looking at when that happens. You're seeing light that is older than the Egyptian pyramids, older than ancient Rome, older than basically every human civilization that has ever existed on this planet. That light didn't just travel 93 million miles across the vacuum of space to reach you. It spent somewhere between 10,000 and 170,000 years fighting its way out of the interior of the sun before it ever even touched the void of space. And the fact that you can see it right now, sitting wherever you are, is the result of a process so violent, so incomprehensibly powerful, and so perfectly balanced that it almost feels like it was designed. Almost. The sun has been the center of human experience since before we could even write about it. Civilizations worshipped it. Farmers depended on it. Ancient astronomers tracked its movement across the sky with remarkable precision. And yet for most of human history, we had absolutely no idea what it actually was or how it worked. We knew it was hot and bright and essential. We knew that if it disappeared, we would all be dead within a week. But the internal mechanics of the thing, the reason it burns, the reason it hasn't burned out yet, the reason it produces the exact type of light that life on Earth needs to survive, all of that was a complete mystery until shockingly recently. And now, thanks to a new generation of spacecraft that have gotten closer to the sun than anything we've ever launched before, NASA has started pulling back the curtain on what's actually happening inside that enormous ball of plasma. And what they've found is genuinely stranger, more fascinating, and more connected to your existence than most people ever stop to think about. So let's go through it from the very beginning. About 4.5 billion years ago, the region of space where our solar system now sits was just a massive, cold, mostly empty cloud of gas stretching across hundreds of light years. This cloud was mostly hydrogen and helium, but mixed in were heavier elements like carbon, oxygen, and iron. And those heavier elements didn't come from the Big Bang. They came from stars that lived and died before our sun was ever born, that exploded at the end of their lives and scattered all of that material across the galaxy like cosmic seeds, which means the sun is, in a very real sense, made out of recycled stardust. The iron in your blood and the calcium in your bones were cooked up in the hearts of stars that died long before our solar system existed. So the next time someone tells you that you're made of stardust, that's not poetry, that's just chemistry. For a long time, this cloud just sat there drifting through the galaxy. Then a massive nearby star reached the end of its life and exploded in a supernova, and the shockwave from that blast compressed the cloud and pushed it into motion. Once that compression started, gravity took over. Denser pockets of gas began pulling in surrounding material, grew denser, pulled in even more material, in a self-reinforcing cycle that over hundreds of thousands of years transformed that diffuse cloud into tight, increasingly hot, increasingly dense knots of matter. One of those knots would eventually become our sun. At this early stage, the object forming at the center of what will become our solar system is called a protostellar core. There's no light yet. Just a dark, collapsing ball of gas that's actually bigger than our entire solar system today, slowly pulling in more material and heating up from all of that inward pressure. This goes on for another couple of million years, and then when the temperature at the very center reaches 10 million degrees Celsius, something happens that changes everything. Something that has never happened in this corner of the galaxy before. Nuclear fusion begins, and that is the moment a protostar becomes a star. It's worth taking a minute to understand what fusion actually is, because it's at the heart of everything else we're going to talk about. A hydrogen atom has a single proton at its center, carrying a positive electrical charge. Like charges repel each other, so under normal conditions, two hydrogen protons will just bounce off one another and go their separate ways. But inside the core of a star, the temperature and pressure are so extreme that hydrogen atoms are stripped of their electrons entirely. All that's left is bare protons flying around at incredible speeds, and at 10 million degrees, some of those collisions happen with enough force to overcome that natural repulsion. When that happens, the strong nuclear force, the most powerful force in the universe at short distances, grabs the protons and holds them together, and a new, slightly heavier atom begins to form. This kicks off what physicists call the proton-proton chain. Two hydrogen atoms fuse into a heavier form of hydrogen called deuterium. That deuterium fuses with another hydrogen atom to form helium-3, and two helium-3 atoms eventually combine into helium-4. This chain of reactions accounts for about 99% of all the energy the Sun produces. And it has been running continuously, without stopping, for 4.5 billion years. Here's where Einstein comes in. When you add up the mass of the hydrogen atoms that go into this fusion process and compare it to the mass of the helium that comes out, there's a discrepancy. A tiny amount of mass seems to vanish at every step. But it doesn't disappear. It converts directly into energy, which is exactly what E equals mc squared describes. Energy equals mass multiplied by the speed of light squared. And because the speed of light is roughly 300 million meters per second, squaring that number gives you an almost incomprehensibly large multiplier, which means even a minuscule amount of vanished mass produces a staggering amount of energy. Every single second, the Sun converts about 4 million tons of its own mass into pure energy through this process. It has been doing that every second for 4.5 billion years, and it will keep doing it for roughly another 5 billion before it starts running low on fuel. What's especially elegant about this whole system is how it regulates itself. As the fusion reactions ramp up and produce more energy, that energy pushes outward from the core against the crushing inward pull of gravity. When those two forces find their balance point, the star stops collapsing and settles into a stable size. Scientists call this hydrostatic equilibrium, and our Sun has been sitting in that perfectly balanced state ever since fusion first ignited. It's essentially a self-correcting system. More fusion means more outward pressure, which slows the collapse, which reduces the pressure on the core, which cools the fusion slightly, which lets gravity compress it again just enough to ramp the fusion back up. Back and forth, continuously, maintaining that balance for billions of years. Now, once energy is produced in the core, you might assume it shoots straight out to the surface and into space relatively quickly. But the reality is one of the most counterintuitive things about the Sun. The interior is so extraordinarily dense that photons, the fundamental particles of light, cannot travel in straight lines through it. They move a tiny distance, collide with another particle, get absorbed, and then get re-emitted in a completely random direction. Then it happens again, and again, thousands of times per second, for thousands of years. Scientists call this a random walk, and it means the path a photon takes from the core to the surface looks nothing like a straight line. It looks more like the completely chaotic wandering of someone stumbling through a pitch-dark warehouse that's completely packed with other people also wandering in random directions. This journey takes between 10,000 and 170,000 years on average. Then, once a photon finally reaches the surface, it crosses the 93 million miles to Earth in just 8 minutes. 10,000 years to cross the interior of the Sun, 8 minutes to cross the rest of the way to our planet. The inside of the Sun is genuinely the most impressive traffic jam in the known universe. And while photons are making that agonizingly slow journey outward, they're also transforming. Deep in the core, close to the fusion reactions, photons carry enormous amounts of energy and vibrate at incredibly high frequencies, well beyond what the human eye can detect. They start out essentially as X-rays, powerful enough to cause serious cellular damage. But as they bounce through progressively cooler and less dense layers of plasma over those thousands of years, they gradually lose energy and slow down. By the time they finally escape from the surface into space, they've transformed into visible light and gentle ultraviolet radiation. The exact wavelengths that power photosynthesis, the light that warms the oceans, the light that your eyes evolved to detect. That transformation isn't an accident. It's a direct consequence of the Sun's size and internal structure, and it's part of why life as we know it is possible here. The Sun itself is structured in distinct layers, and understanding those layers is key to understanding why the Sun behaves the way it does. At the very center is the core where all the fusion happens. It occupies roughly the innermost quarter of the Sun's radius, but contains about half its total mass. The temperature here is 15 million degrees and the pressure is 250 billion times what you'd feel at the bottom of Earth's deepest ocean. Nothing we've ever built could survive there for a fraction of a second. Moving outward from the core is the radiative zone, the thick region of dense plasma where photons spend the vast majority of that long, wandering journey toward the surface. The material here is so dense it's essentially opaque, and energy can only move outward through that endless process of absorption and re-emission. Then, at about 70% of the way from the center to the surface, something changes. The material becomes cool enough that electrons can start reattaching to atoms, which makes it less opaque. And when that happens, a completely different mode of energy transport takes over called convection. You've seen convection in your own kitchen. Heat water on a stove and the hot water at the bottom rises, cools at the surface, and sinks back down in a circulating loop. The same thing happens in the sun's convective zone, except instead of water you have plasma at temperatures of around 1,000,000 degrees, and the convective cells are enormous. Each individual churning bubble of rising plasma is roughly the size of Texas, and there are about 2 million of them covering the surface at any given time. From the right instruments, you can actually see this granulated pattern on the sun's surface, a constantly churning mosaic of rising and falling plasma covering the entire visible disk. Above the convective zone is the photosphere, what we think of as the visible surface of the sun. It's not a solid surface. There's no ground to stand on. It's the layer where the plasma finally becomes thin enough for photons to escape into space without being immediately reabsorbed. The temperature here drops to around 5,500 degrees, which is still extraordinarily hot but almost cool by solar standards. The photosphere is also where sunspots appear. These are darker, cooler regions where intense magnetic fields suppress the normal upward flow of heat from the convective zone below. Sunspots follow a roughly 11-year cycle in terms of how many appear at once, and that cycle turns out to have real consequences for Earth in terms of space weather, communication disruptions, and satellite operations. Above the photosphere is the corona, the outer atmosphere of the Sun, and this is where one of the biggest unsolved mysteries in all of solar physics lives. The corona is somewhere between 1 and 3 million degrees. Which sounds like it should make perfect sense given that we're talking about the Sun, until you realize that the surface just below it is only about 5,500 degrees. The further you get from the source of heat, the hotter it gets. That's the opposite of how heat is supposed to work, and for decades nobody had a satisfying explanation for it. Recent data from NASA's Parker Solar Probe, which has actually flown directly through the corona, getting closer to the Sun than any spacecraft in history, has started to illuminate what's happening. The probe detected what appear to be enormous numbers of tiny magnetic reconnection events, essentially miniature explosions where stressed magnetic field lines snap and reconnect in a lower energy configuration, releasing bursts of energy into the surrounding plasma. The current leading theory is that millions of these events, individually too small to detect, are collectively depositing enough energy into the corona to maintain its extreme temperature. It's a compelling explanation, but we still don't have the complete picture. The coronal heating problem remains one of the most actively studied open questions in solar science. The corona also matters because it's where the solar wind originates. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the Sun in all directions at hundreds of miles per second. It fills the entire solar system constantly, and where those particles encounter a planet, interesting things happen. On Earth, our magnetic field deflects most of the solar wind around the planet. Without that protection, the solar wind would gradually erode our atmosphere the same way it stripped Mars of most of its air billions of years ago. The fact that Earth has maintained a strong magnetic field is one of the less celebrated but absolutely critical reasons that life exists. Here, when the solar wind does interact with Earth's magnetic field near the polar regions, it produces the auroras, those extraordinary curtains of colored light visible from high latitudes. Charged particles follow the magnetic field lines down into the upper atmosphere, collide with air molecules and cause them to glow. Oxygen glows green and red. Nitrogen produces blue and purple. The result is one of the most visually spectacular natural phenomena on the planet, all ultimately caused by the Sun's outer atmosphere shedding particles into space. But the Sun doesn't always shed particles gently. Sometimes it erupts. Coronal mass ejections are massive explosions of magnetized plasma from the solar surface that can hurl billions of tons of material outward at several million miles per hour. When one of these is directed at Earth and actually connects, it triggers a geomagnetic storm that can knock out power grids, disrupt GPS systems, damage satellites, and produce auroras visible from much lower latitudes than usual. The most powerful solar storm in recorded history, the 1859 Carrington event, was strong enough to set telegraph wires on fire and produce auroras visible from the tropics. A storm of that magnitude hitting Earth today would be genuinely catastrophic for modern infrastructure in a way that's difficult to fully quantify. Understanding the mechanisms that drive these events and building better systems for predicting them is one of the central goals of current solar research, and it's a big part of why missions like the Parker Solar Probe matter beyond pure scientific curiosity. Looking further down the road, the Sun's story doesn't end with steady, stable fusion. In about 5 billion years, the hydrogen fuel in the core will be largely exhausted. The balance between gravity and outward energy pressure will break down, and gravity will start winning again, compressing the core. That compression will heat the layers of hydrogen surrounding the core enough to ignite fusion in a shell, and the energy from that shell fusion will cause the outer layers of the Sun to expand enormously. The Sun will become a red giant, swelling to a size large enough to engulf Mercury, Venus, and possibly Earth. And long before the Sun physically reaches our planet, the oceans will have boiled away, the atmosphere will have been stripped, and the surface will have been scorched beyond any recognition. That's about 5 billion years from now, which is longer than Earth has existed up to this point, so it's not exactly a near-term concern. But it's a useful reminder that the Sun we see today is not a permanent fixture. It's a middle-aged star in the middle of its main sequence, with roughly as much life left ahead of it as it has already lived. After the red giant phase, the Sun will shed its outer layers in an expanding shell of glowing gas, leaving behind a dense, Earth-sized remnant of the core called a white dwarf. No more fusion, just a slowly cooling ember radiating away its stored heat over billions of years. Quietly fading from a star that once powered an entire solar system into something cold and dark and still. But here's what I think is the part that actually matters when you step back and look at all of this. The Sun isn't just an interesting astronomical object sitting in the background of our lives. It's not scenery. Everything about your existence is directly downstream of what happens inside it. The warmth that keeps liquid water stable on Earth's surface. The light that drives photosynthesis and feeds essentially every food chain on the planet. The magnetic environment created by the solar-wind interaction that helps protect our atmosphere. Even the atoms your body is built from, the carbon, oxygen, calcium, and iron, were produced inside stars that lived and died before our Sun was born, and the Sun itself was assembled from the debris of those earlier generations of stellar evolution. You are not separate from any of this. You are a product of it. The nuclear reactions running in the core of the Sun right now are a continuation of the same physical processes that built the atoms in your body billions of years ago in the cores of other stars. The light coming through your window started its journey as a fusion reaction in conditions that no human technology can replicate, spent thousands of years working its way out through layer after layer of dense plasma, and arrived at your eyes in exactly the wavelength range that life on this planet evolved to use. NASA's newest solar missions keep reinforcing just how much. We still have to learn. The Parker Solar Probe and the Solar Orbiter are sending back data that's already forcing revisions to models we thought were pretty solid. The magnetic behavior of the corona is more complex than predicted. The structure of the solar wind is different from what earlier theories suggested. The small-scale dynamics of the photosphere are stranger and more intricate than we expected. Every new observation reveals something that doesn't quite fit the existing framework, which means the existing framework has to grow to accommodate it. And that's exactly how science is supposed to work. So the next time you step outside on a clear morning and feel that warmth on your face, take a second to actually think about what you're experiencing. You're receiving energy that began as a tiny discrepancy in the mass of hydrogen atoms, amplified by the speed of light squared into an enormous release of radiation, that then spent thousands of years bouncing randomly through one of the densest environments in the solar system, before finally escaping and crossing 93 million miles of empty space in 8 minutes to land on you. All of that happening continuously, every moment of every day, because 4.5 billion years ago, a dying star somewhere in this galaxy exploded, and the shockwave found a cloud of gas, and gravity did the rest. It's a lot to think about over your morning coffee. But that's kind of the point.